SwayamPrabha. Digital India. Educated India.
Welcome. So we are in next module, module 12. So before we formally start this module, I wanted to show you some of the examples related to the previous module. So in the previous module, we learned how to alleviate shear and volumetric locking through one of the two such method mainly we have learned is one is your incompatible mode elements, another is B-bar method. So I will just show some of the examples, and these examples are basically you can always test in your finite element code so that you can also validate through these examples, because some of the examples are obviously having the exact solution. For instance, we learned what is the incompatible mode element, that is QM6 element, that is modified 6 modes, that is your incompatible modes we consider. In 2D, if you have Q4 element, if you incorporate those incompatible modes, that is 1 minus xi square and 1 minus eta square, and then you condensed out those extra constants, which is for 2D it is 4, for 3D it is 9, because in 3D you will also have to consider 1 minus eta, 1 minus xi, 1 minus eta, and 1 minus you take anything gamma square. So or RST in 3D. So there are 9 such constants. So 9 such constants you have to condensed out, and the 3D stiffness matrix will be your 24 by 24 for 8 noded element. But your finally you have to compute the inverse of 9 cross 9 matrix. While in 2D you have to take the inverse of 4 cross 4 matrix, which constraints which is corresponding to the constants, that extra incompatible constants which we need to we have learned that. Now to check how these incompatible modes behaves, because we have already learned that these incompatible elements produced, actually I have shown some of the analytical example where we have also seen that these incompatible modes, if you include in Q4 element, for instance 4 noded by quadrilateral element, then you can exactly represents the bending mode. So this is one example, thin cantilever plane stress beam, where this is a cantilever beam. So in this beam we apply a moment, essentially a sigma xx, or the stress along the x direction, and then this stress profile is very familiar to us for our from our knowledge of solid mechanics or advanced solid mechanics, whatever you call. So this stress profile we apply at the end of the free end of the cantilever beam, and then we consider a length is 10 unit. It can have millimeter or any other unit corresponding. So 10 unit, and h is 0.1 unit. So h by L ratio is 0.01, that is L by H ratio is 100. So it is really a thin category beam, even though the picture is not drawn in the scale. So now this traction force obviously is sigma dot n, so among which only sigma xx is given to the free end of the beam. Now, if I consider the plane stress constitutive relation, that means your 2D plane stress, that is E is E minus E by 1 minus nu square 1 nu 1 and 1 minus nu by 2. So, that constitutive equation if I consider, then the exact solution can be written in this form. So, this exact solution is coming from the 3D elasticity or 2D elasticity governing equation, that is del dot sigma without body force, that is del dot sigma equals to 0, and with the boundary condition. So, we know the boundary condition, that is this is a plane cantilever. So, at this point, that is if I consider x equals to 0 0, at this point it is fixed, and other points it is restricted movement along x direction. So, now if I solve this problem with the standard 4-noded element, for instance the quadrilateral element, then what will look if I use the 25 cross 25 element, 25 cross 4 element, then it looks like this. This is the solution. This so this just a second, yeah. So, this is the, if I solve with a 25 cross element 4 element, then the bending deformation or the deflection of the beam is like this. Now, while the exact solution, this is my exact solution. So, now here instead of 25 cross 4, if I increase the number of element, for instance instead of 25 4, if I use 400 cross 4 element, then we can see that solution approaches near the exact solution, but still it is not exact. So, there are some deviations from the exact solution. On the other hand, if you use quadratic element, that is Q8, that is 8-noded quadrilateral, then you can approach the exact solution very easily. But in the volumetric or on the shear locking part, that our objective is how to get the accurate solution with the lower order elements. For instance, this is the V displacement. You see that V displacement is also not matching for 25 cross 4, that is 25 in the length direction and 4 in the height direction of the beam. Now, this beam is actually as we know, that is L by H ratio is 100. So, it is a really thin beam. Now, you can see that performance of the standard quadrilateral in the coarse mesh is very bad, and it is not acceptable as in solution for our purpose. Now, instead of using the 4-node quadrilateral element, if I use or if I include the incompatible mode into it, for instance, the same standard 4-noded quadrilateral element with the incompatible mode, that is my if I consider my UV as something like this, that is U is your standard Ni Xi Ui, that is your I equals to 1 to 4, that is standard 4-noded quadrilateral, plus your N5 Ni alpha I if I consider, then I equals to 5 to 6. Similarly, V is, I can also take summation of Ni Ui, Ni Vi, I equals to 1 to 4, and then summation of I equals to 5 to 6 Ni alpha or beta I. So, these alpha beta are 4 constants, and N5 and N6 are 2 incompatible modes. So, N5 is 1 minus I square and N6 is 1 minus eta square. So, if I include these modes in the standard Q4 element, that is known as the QM6 element, even though we discussed this thing in the details in the previous module. So, this is QM6. Now, here these alpha beta, they are independent of the nodes. So naturally it is not nodal dependencies there. So if I use this incompatible mode, then you can see that with the 4-noded quadrilateral, even with the 4-noded QM6 element with the 25. So here we keep the mesh constant. So with this 25 cross 4 more element, we have the exact result with the finite element solution, and the FEM with incompatible mode matches exactly. So this is the advantage of using incompatible mode. So similarly, the V displacement also you can see that it matches almost exactly with the finite element solution, and the analytical or exact solution matches exactly. So so this is the main advantage of using incompatible mode. This so naturally in this thin structure, obviously one way of using the lower order element and incompatible modes, and otherwise we have to go the polynomial refinement, which is known as the order of polynomial increase in order of polynomial. That means that you use higher order element like 8-noded quadrilateral element. There also you can observe the closeness with the exact solution. Now similar observation, if I use the 8-noded, even though 8-noded element is not formally introduced, if I use the 8-noded element for 3D, then also actually you can observe the same phenomena in bending. Now so this is one example I wanted to show, so that what is the purpose of incompatible modes and how it is effective in solving some specific problem that is described in this example. Now we have also learned the B-bar method, which is to avoid the volumetric locking. So I will show some examples of the B-bar method, because B-bar method is essentially a strain projection method. So let us see some example with the B-bar method. So the first problem is fully constrained 2D block. So in this block example, the exact solution is actually given here. So this is a lambda by mu parameter, the Lamy constants. The first Lamy constant is lambda and second Lamy constants are mu. So this lambda mu parameter is mu is 40. So as per Poisson's ratio, we can choose the lambda. So I will come to that. So now this block is fixed from the all 4 sides, that is uv displacement is 0, and there is a body force into it, and this body force is given by the some analytical solution, analytical function. So this q qx and qy are 2 body force acting on this block. So in this block the boundaries are fixed, so that is no deformation is allowed, and the mu is given as 40. So depending on the how you choose lambda, your the constrainment or the incompressibility will vary. So if you look carefully, this block, if you take the volumetric strain of this block, that is del u del x plus del v del y, this thing is actually 0. So that means it is totally incompressible element, incompressible block. So that means if I wanted to solve this with the standard finite element, say 40 cos 40 mesh, so x direction 40 and y direction 40, if I want to solve, then let us see what is the performance of the standard Q4 element. So if you see that the exact solution, now lambda by mu ratio is I have taken 10 to the power 6. So that means lambda is essentially 10 to the power 6 into mu, that is mu is the shear modulus. So shear modulus we have taken 40, so 40 into 10 to the power 6 is my lambda. So corresponding to that, the Poisson's ratio is 0.49999. So it is almost incompressible. Now, if you use the Q4 element, then you will see that your displacements are of this form. Now, the exact solution where it is 0.096 because it is totally incompressible block. Now, if you use with the B-bar method, then you can see that your result is much more closer to the exact solution compared to the standard Q4 element. So, B-bar method actually plays here for the incompressibility constraint. So, this is one example where B-bar method is useful for simulating finite element this thing, and you will not able to get the mesh refinement. With the mesh refinement, you will not able to alleviate this incompressibility constraint in this problem. So now this is the V displacement. So same thing, the deformation is actually deformation pattern. So it is plotted on a deformed mesh. So deformation pattern is very similar to the exact solution. So exact and deformed mesh are very much close with the B-bar method, but while Q4 element, that is standard 4-noded quadrilateral element, it is not matching at all. So now instead of 10 to the power lambda mu 10 to the power 6, if I just increase it to say 10 to the power 12, then what happens to it? Naturally, if I use 10 to the power 12, then you can see that it is fully almost in numerical precision, it is almost incompressible. That is, Poisson's ratio is 0.5 10 to the power minus 12. So now in this case, if you see, then you will see that it is actually 0. So even though the shapes are, the contours looks like this, then you will see that U displacement is actually 10 to the power minus 10 and 10 to the power minus 10. So what is actually happening here? If you use Q4 element, then incompressibility constraint or the volumetric part of the matrix, constitutive matrix, acts as a penalizer. So that penalizer penalizes the zero displacement. So the deviatoric displacement doesn't come up in the solution. So that's why we say that it is the mesh is locked here, so that the displacement is not displacement or the pressure or displacement is incorrect. So that's why we need to use B-bar method here to get this. So if I use B-bar method, you can see that this is actually the strain projection method. If you see that it is matching with the exact solution. So similar observations we can have for V displacement, that if I use B-bar method, then my displacements or the deformed mesh is very much close to the exact solution, while if I use the Q4 element, then it is not exact, it is actually zero displacement. So that means the mesh locking happening or the volumetric locking present in the solution. So this is the example, or this is the advantage of the B-bar method. Now in the next example, we consider the same cantilever bit but not a thin beam here. Here H by L ratio is 0.1, that is L by H ratio is 10, when the same T max is 10 and Young's modulus is 200, and Poisson's ratio is instead of 0.3 I have taken initially, which was a plane stress problem. So now we are taking 0.499. So it is a very incompressible regime. And now the solution is obviously in the plane strain domain, so that we can have the effect of incompressibility, because we know the plane strain constitutive equation where 1 minus 2 nu term comes, and because of the 1 minus 2 nu terms goes 0, so that means that bulk modulus goes to infinity. So now the exact solution looks like this. So here basically if you substitute the E bar with E into 1 minus nu square, and nu bar is nu by 1 minus nu, you will get this solution, because it is a conversion of plane stress to plane strain. So now this is the E is actually E bar and nu bar. If I, so that means this quantity is actually 1 by E bar, and this is actually nu bar. So Now this is a plane strain problem. Now what happens if I simulate with the standard say 4-noded element? So let us see. Now if you see that if I use the standard 4-noded element, then this is my exact solution, and this is the solution with the upper portion, that is this this solution and this solution, that is u and v displacement are plotted in the deformed mesh. It looks like this. So that means it is far from the exact solution. On the other hand, if I use B-bar method or the strain projection method, then it matches with the exact solution, even with the 25x4 mesh. So this is on the 25x4 mesh. It matches with the exact solution very much. So that's why while in the limit of incompressibility, actually you have to use a different or modified element so that it can cater the constraint in the solution. So this is one example. So now if I plot the volumetric strain, you can see that it is with the B bar, it is close to the exact volumetric strain and other things. So this is very similar for the previous thing. Now our next problem, if I would like to show you, is one Cook's membrane problem. So this is a famous problem. This is always used to validate finite element codes. So here also we have taken the E is 200 GPa or 200 unit, or 0.499 is the nu, and this is a actually Cook's membrane. So it's a cantilever kind of beam. So here the dimension is 44, 48, and there is a traction vertical along the right edge. There is a vertical traction, so which is Tx and Ty. So Tx is 0 and Ty is 10 unit. So if I apply this, and if I apply with some mesh with the finite element, standard finite element mesh, then let us see how Q4 performs. So you can see that Q4 element, this is U and V displacement. This Q4 element performs very poorly, where the bending phenomena is truly observed in the B bar method. So you can see V displacement and U displacements are very much different in the Q and Q4 and Q bar, Q4 with B bar method. So the basic, again, the same advantage of using the strain projection method, because approximating the volumetric strain properly, so to alleviate the constraint of volumetric incompressibility constraint, so that the deviatoric component of the solution pops up. So that's the main objective. Now instead of 0.499, if I again increase the Poisson's ratio, then you will see that there is no bending at all observed in Q4 element. On the other hand, Q4 with the B bar, the solution doesn't change much. So that means that incompressibility, because solution will not change much, because there is no volumetric part of the solution. The main part of the solution is the deviatoric part. So that means volume remains constant, but only the shape or the distortional part is effective. The shape change is happening. So that means the Poisson's ratio, I'm just taking 4.4999. So that means 0.5 into 10 minus 10 to the power minus 6. So that's the so that means the in some incompressible elasticity, to solve incompressible elasticity problem, it is not possible to solve with the standard finite element. So you need to have some different kind of modification, some different modification, or some modification of the standard finite element, so that you can solve effectively the incompressible problems. Now if I plot the pressure in this, you can see that Q4 element, the pressure diagram is very pathetic compared to the, even though we have smoothed the pressure here. So here with the B bar method. So that means naturally we should use a modified element while solving the incompressibility of the incompressibility, where the incompressibility constant present in the problem. So now in the next example, I just wanted to show another one last example where a nearly incompressible 3D block is under compression. So basically you can consider a block and this block is actually 4 by 4 block, and there is a pressure applied in this distance is actually your 1, this is actually 1 and this is actually 1, even though the diagram may not be in scale. Okay, so so this is actually, this is not there, so this is 1. So now in this case, instead of solving the full problem, we can use symmetry and solve the problem. So what I did is I just choose the 1 octant of the 1 octant of the block and simulate it. So naturally the symmetric boundary conditions will play into these phases, and then this at W will be 0. So this is that the bottom face of this block will be W will be 0, and in the top face U and V are 0 at Z equals to 1. So that means, so again this is also your I think 1, right? So this distance is actually 1. So now this is 2, I believe. Okay, right? So basically this is 1, this is 1, and this is 1. So basically 1 cross 1 block. So now I think it is 2 by 2. Okay, this block is 2 by 2. So yes, 2 by 2 block instead of 1 by 4 by 4 block. So 2 by 2 block. So this is 1, this is 1. So now if I simulate with the 4-noded or sorry 8-noded standard quadrilateral element, then what? So this is the solution of the block. Now if I use the standard 8-noded element, for instance the brick element or hexahedral element, which is also known as the P8 element, parallelogram element. Okay, so even though this element we have not read it, we have not studied it yet, in this module we will study this. So this is similar, just an extension of 2D problem, 2D elements. So there is 8 nodes. So 1, 2, 3, 4, 5, 6, 7, 8. So this is the element. So if I use 8-noded element, then how it will look like is this. So if I use P8 element, then it will look like this. On the other hand, if I use P8 element with the B-bar method, again B-bar method we have studied for 3D problems, so it is just an same thing. So if I use P8 element, you see the block is very much proper, deformation is proper compared to the P8 element. P8 element will lock. So that means volumetric locking in the P8 element will be there. Now if I just plot the W, then W will look like this. So naturally you see that with a very high Poisson's ratio, if I take, then the solution goes to naturally 0, while in the B-bar solution is like this. So naturally the B-bar and B-bar method is very useful in solving the incompressibility problem. So this is the all 4 or 5 examples that I wanted to show that what really actually means by learning those advanced topics to alleviate shear and volumetric locking. So what is the use of this? So naturally these examples you can also program to check your finite element code, and obviously this is not the end of this topic. There are some advanced topics also there. For instance, the most general way to solve or this kind of locking problem is to use the hybrid or mixed formulation, where stress or strain is also interpolated or approximated independent of the displacement approximation or displacement interpolation. So that is a mixed formulation or mixed finite element formulation or hybrid finite element formulation. So there are two important variational formulations for this kind of finite element. One is Hellinger-Resner, that is two-field variation formulation. So that can be based on displacement pressure, that can be based on displacement stress, that can be based on displacement strain. So three kind of Hellinger-Resner formulation is possible. So that is two-field variational formulation, which is known as Hellinger-Resner variation formulation. So that is advanced topic. Another one is Hu-Wasiju variational principle, which is three-field variation principle, which involves in, for instance, displacement, stress and strain, or displacement, volumetric strain or stress. So something like this. So that means the main issue is here that in displacement formulation, we stress is a derived quantity from the displacement, and naturally in elasticity it is a derived quantity from the displacement. So from displacement we get strain, then we multiply with the constitutive relation to get the stress. But in numerical simulation, instead of considering this stress or strain as derived quantity, instead of that, if we interpolate these stress and strains and then solve the finite element problem, then we get the mixed formulation or variational formulation, which is involving two or more variables. But again, this need not to be always correct, that there is a conditions, or for instance there is a limitation principles how we can achieve this. So those are advanced topic, those you can also learn, those who are interested in this field. Now so with this thing I stop today. So our main objective is here to show you some of the example problems for which you can also use these analytical solutions to check your finite element code. So how it performs, whether your code is correct or not. So that's all. So I stop here. We'll meet in the next lecture. Thank you.